Right, good morning, good afternoon. Hello to those who might be watching this after the fact. We want to welcome you to our Data for Nutrition webinar series on survey sampling strategies. And today we're going to be hearing and talking about geospatial sampling with the simple spatial survey method, known as S3M. Next slide. So just before we start, just want to give you some kind of ground rules for how we run these webinars. You'll notice that all your video and microphones are muted during the presentations. So we ask you to use the Q&A button to submit your questions for the panel or for our speaker. We're going to get to as many questions as we can, and I actually think we'll have some good time to have a discussion with those who are joining us. A recording of this webinar will be available immediately on the Data for Nutrition YouTube channel. And then in about a week, we'll have the slides and a Q&A summary posted to the community. If you're having trouble at any point, please use the Zoom chat to reach out to Riley Hour by selecting all panelists, and we'll do our best to respond during the webinar. I saw one message that there's an echo, which I'm not hearing, but perhaps, Riley, you can address that. Next slide. So just to tell you, the Data for Nutrition Community of Practice is a community of practice that provides members with opportunities to share knowledge, experience, and questions relevant to strengthening the nutrition data value chain at all levels, from national to local, in order to achieve better nutrition outcomes in low and middle income countries. And since launching in early 2020, we have more than 863 members and continue to grow. So I'm going to be the moderator today. My name is Rebecca Heidkamp, and I'm an associate scientist at the Johns Hopkins Bloomberg School of Public Health, and I lead an initiative called Data Dent that is really relevant to this topic. Next slide. And just to make note, so this is going to be the first webinar in what we hope to develop out to be a sampling strategy series. And we'll be telling you a little bit more about some of the webinars we're hoping to have. But we know that household surveys are a primary source of nutrition data in many low and middle income countries. And sometimes we don't really think about the fact that these fundamental decisions about things like sampling methods can have really big implications for the cost and for the ways that we're able to use data. So our goal here is to really try to examine different methods for household survey sampling and to understand why they might be preferred in different use cases. And so really would love to encourage, if any of you who are listening have a relevant method or an experience related to this that you'd like to share, please reach out to us, because we'd love to find a way to share that either via a webinar or some of the other outlets we have through Data for Nutrition. So moving on to today's speaker, we're really thankful to have Mark Myatt, who is a consulting epidemiologist with his organization Brixton Health. And he's been for many years a technical associate with the Emergency Nutrition Network. I think it's a very familiar name to many of you who have worked in emergency nutrition, but for some of us who aren't as engaged in that community, I think you're going to find Mark's knowledge and his experience to be really engaging and compelling. So without further ado, I'm going to hand over to you, Mark.
First slide, please. So what we're going to do is we're going to have a little bit of review as to why we might want to have a spatial dimension to our survey data, and sort of ask the question and answer the question is that if we ignore a spatial dimension of the data, do we lose any important information, or is any important information hidden in the sample? And we'll look at two simple spatial survey methods. The absolute simplest method, the centric systematic area sampling method, and another one that's based on that, but not quite as simple, but very much improved, the simple spatial survey method, S3M. Next slide, please. So now the first bit was why spatial. So I think there are questions we need to consider. And I'm an epidemiologist, and since I was a child epidemiologist, a training epidemiologist, I'd always been taught that there were three key variables in any epidemiological study. or description, and they were time, place, and person. And these answer the questions when, where, and whom. Now, the survey methods we've been using in emergency nutrition and development, such as SMART, MIX, DHS, and similar surveys, we have a time variable, and that's the time when the survey was done. And if we want to look at change over time, we do another survey, so we can show change over time. Person, they're the subjects, the survey subjects, the survey respondents, and usually that's the sole definition in these survey designs that we have for representativeness. Place, we seldom have place. That the sample is designed to provide an estimate over quite a large area, the survey area or the district or the state. And these are large and politically defined areas, and we have samples within each of those large and politically defined areas. But there's no fine grain, no high resolution spatial definition of the presentational results. Our variables now, our indicators are need and coverage. And we answer questions, what? So what is the coverage? What is the need? And the barriers, bottlenecks, and boosters from coverage surveys answer the questions, why is coverage good, and why not? Why is coverage not good? Next slide, please. So we have to ask ourselves, I think, that given that we have mature and well-accepted survey methods, and we've got organisations that roll those survey methods out internationally, is this lack of the spatial dimension, spatial resolution, is that important? And I would say it's not important if the variable of interest is similar over the estimation areas. And I don't think that's true of many variables. You know, I think it's true if I'm thinking of particularly of variables that are associated probably with an infection process, which would include wasting, which is an infection process is spatially clustered, so you'd expect spatial clustering of wasting. And coverage, we don't expect to have homogeneous coverage across the entire program area. And that's very likely to be true of centralized programs like the old therapeutic feeding style, therapeutic feeding center style programming. Might be true of late stage CMAM, CTC programming, but unlikely to be true during startup or expansion. And it's during startup and expansion you want to be able to identify problems with coverage, usually. And if coverage is uneven, it's useful to be able to identify where and why the coverage is good and where and why the coverage is poor. And these are spatial questions. Next slide, please. So let's have a look at it's a rather extreme example of uneven coverage. And in this particular long, narrow principality, we have an overall coverage of 50%. Coverage is 90% in the western side of the principality, and 10% in the right-hand side, on the eastern side of the principality. The overall coverage is roughly 50%, but where is this coverage 50%? I can't see any place on that broad map where coverage is 50%. So I wonder what a 50% coverage might mean in this context, or is it a meaningless estimate? It's a very difficult thing to pin down. So in this case, we've got no single central tendency in the coverage. So the average is, I think, without meaning. And I think what happens is that average, it hides excellent performance, 90% coverage, and poor performance, 10% coverage. And it's hidden by this 50% average, which is roughly, you know, in the sphere standards for a therapeutic feeding program, that is the minimum standard. You know, that's you think you might be we're doing reasonably well, but in fact, you're doing very well in one part of this area and very badly in another. And so the central tendency is obscuring the meaning of the data, hiding reality, the spatial reality. Next slide, please. So there we got that 50%, which is more useful to us. I think The second map there is more useful to us, where it shows the spatial distribution. And we're back to that same question, is that the 50%, where is that 50%? It doesn't seem to locate anywhere. And what does it mean? I don't think it means anything. Next slide. So in many cases, and particularly where the indicator of interest is not spatially homogeneous, is not the same everywhere in the survey area, that without a spatial dimension to our data, spatial dimension to our sample, we don't get the full picture. Slide, please. So we started off by saying we would look at simple survey methods, simple spatial survey methods. And I think we've got to ask, say, why simple? Because in the nutrition field, that I think there is a saying that is, why go for something simple when you can have something complicated instead? Why go for something cheap when you can have something that's expensive instead? But I think we've got to look at our typical implementing partners for our child survival programming and our growth monitoring and promotion programming. And these are local ministries of health, local international NGOs, and United Nations organisations. And these organisations seldom have staff with the capacity required for delivering complicated survey designs. Sometimes they do. Say an organisation like UNICEF has capacity, but that capacity might be in headquarters, and they would generally put that capacity out into the field as needed. I think we have to remember that geostatistical expertise is that's usually people with geostatistical expertise usually do most of their work for oil exploration, mining companies, and it's expensive to buy these people in for humanitarian work, and even if you could afford them, it's an expensive job. So cheap and simple is what we want, and so we'll look at cheap and simple. Next slide, please. So the simplest method is a centric systematic area sample, and that's the most difficult thing to remember that title. And here it is. So it's as easy as find a map, draw a grid over that map, and each of those grid squares is now your mapping area or estimation area. We select the squares that we're going to take a sample from, and in this case we're using squares in which 50% of the area, more than 50% of the area, is inside the map that we want to be surveying, the mapped area we want to be surveying, and then we take the first stage sample. Now this is rather like a cluster sample, and unfortunately this fourth square in the diagram here has got a little bit distorted. But what we do is we take the community, or the communities closest to the center of each of those squares, and that's where it's centric. If it were not in the center of the square, it would be an eccentric systematic area sample. So there's a slight problem with that image there. Then we do the survey, and we can either do an equal probability selection method in the primary sampling unit, or we could do an exhaustive case finding in the primary sampling unit. In the coverage surveys, we've used active and adaptive case finding because that tends to be very efficient and very fast exhaustive method. We record the data, we do the calculations, and the calculations are quite simple, and then we plot the results. And we can do this by hand with tally sheets and crayons. And so that's about as simple as it gets. And here's an example output. This is from a C-MAN program delivered by a UK-based international NGO, Save the Children UK, in a province, I think, of Niger. And this is Maradi. And we can see here that it's actually, this simple method has provided us a map of point coverage, that's and period coverage. Period coverage includes coverage of cases that have been malnourished but are no longer malnourished but are not likely to be discharged from a program. And point coverage is the coverage of children who are currently severely malnourished. And we can see here that we don't have spatial homogeneity, that if we'd have just done a survey of the entire program area, we'd have got an answer of something like 18% coverage for point coverage. And we know the coverage, that 18% coverage, we know that's not particularly good coverage. But we can see here that there are actually areas of extremely poor coverage. In the north and the northeast, there are areas of zero coverage. And in the south also, there are areas of zero coverage. And other places where coverage is reasonably high. What's happening here is we can see that where you're close to a site or you're close to a road that goes between sites, coverage is quite good. But once we get away from sites and away from main roads, we're actually not achieving the coverage that we would hope, which would be a coverage over 50% in every single square. And we're not seeing that. So using a spatial sample here, we've learned something about how our program is operating in terms of the spatial organization of the society that we're delivering in. Next slide. Now, CSS was used for about a decade, and it was used for monitoring and evaluation of CTC and CMM programs. And after about a decade, people wanted it to do something more or to do it cheaper. And what it was that we wanted it to do larger areas at equivalent cost. And so we developed the simple spatial survey method, S3M. Next slide. What happens here is that we have a centric systematic area sample, except we're centering the sample on the centers of an hexagonal grid. And this creates a triangular network. And what's interesting about using the triangular network is that, as opposed to a square network, is that in every direction you look, the distance between sampling points is similar. Whereas on a simple grid, if you look in the north-south direction or the east-west direction, the distance between each sampling point is one, the equivalent of one side of the square. Whereas if you were to look in the diagonals, so northeast, southwest, and so on, that the distance between each point is about square root 2 sides, so 1.4 sides. So it's not though it looks even and it feels even, it's not entirely even, but the S3M sample, this hexagonal grid sample, gives us a much more even distribution of sampling points. And drawing hexagons is not terribly easy, but you can actually locate the hexagon centers on the corners of a rectangular grid, skipping each one in the north-south direction and the east-west direction. And so it becomes quite simple to draw the sample. Now, having this triangular grid, that what we can do is we can use the 3 points on the vertices of each triangle, the corners of each triangle, as our data to estimate the value inside the triangle. And this gives us more support for the error estimates. In the S3M sample, we only had one sampling point in the center of each square to represent the area that was covered by the square. Now, usually because we were using efficient sampling methods, we could do 2 or 3 villages close to the center of each square. But this way that we can do the same thing here, but we actually have 3 points versus a single point. So we've got more support for the estimate that's in the triangular tile, and that gives us improved precision of the local estimates. Next slide, please. Now, also it provides an efficient reuse of the data. So we can have up to 6 times reuse for some estimates. So in the diagram on the top left, in the top left square of the table, we can see that the very central point is actually used 6 times, reused 6 times. And if we were to use, this is if you're using tile-based estimation, but if you do use a spatial interpolation where you're using all of the sample and doing some weighting by distance to create an estimate, a single point with over the surface, then we're using all the points. And so we've got so we reuse data again and again and again. Now, also what it does in the simple tile-based method is that as we move from one triangle to its neighboring triangle, we still keep some of the data from that previous triangle. So we get an automatic spatial smoothing, as if we were doing, as we would with a moving average of span 3 in a time series. So it doesn't smear out change, but it smooths it away. It smooths out the very high frequency spikes as it does in a time series. What we have here is we have local estimation based on local data. So, and that's even when spatial interpolation is used, because the weights are usually an inverse of the distance. And so the more distant parts don't influence the points in the estimation surface. And we're making a small area homogeneity assumption. We're making the assumption that inside that triangular tile, things are pretty much the same all over that triangular tile, rather than make an assumption that over the entire survey area, things are pretty much the same. One of the good things about this method is it's non-parametric. We're not making any grand assumptions about the spatial distribution of variable under investigation. And there's no need, because we've got more, we've got 3 points for each tile. There's no need for a large primary sampling unit sample size. But we get better precision from the 3 than we do from any single one. Next slide. So let's have a look at the spatial resolution that we get in this sample. So each hexagonal tile in the grid, or in the virtual grid, if you're using a rectangular grid, in the virtual hexagonal grid, has a side, and we'll call that side D. And D is no more than, communities are no more than D away from a sampling point. Let's have a look at if you press the down arrow, you should see another tile there. So here, the area of the triangle is, and that's the formula for the area of an equilateral triangle. And so if D was 10 kilometers, then the area of the tile is 130 square kilometers, and nobody lives more than 10 kilometers from a primary sampling unit. And I think that's a reasonable thing to say, that homogeneity, nobody lives more than 10 kilometers away from a sampling unit, is a reasonable rule. But we have gone for smaller and densely populated settings, such as Rwanda. We've gone for a D of 3, or maybe a D of 5. And in northern India, we've gone for a D of 22. But that's to do with keeping the costs down and accepting the coarsening of the resolution in terms of the tiles. We accept that to keep costs low. Next slide. So here's some examples. This is IYCF behaviours, and here we can see that if we look at good IYCF practices, this is where we can think of this. This is using the ICFI indicator set, but if we were to use the WHO indicator set, we can think that good IYCF practices is people meeting the minimal acceptable diet, the MAD indicator. And we can see here in that top left-hand map, we can see that it's not looking so good. The IYCF behaviours are not looking so good in the southwest corner. And we can see that that's probably due to exclusive breastfeeding not being so common in that location. And we can also look in the middle, on the bottom row in the middle map, we can see that age-appropriate dietary diversity is not as good in that area. So we can see here that there is one particular location, one particular part of the program area where IYCF behaviour is not very good. And we can also see that it's probably due to poor exclusive breastfeeding and to poor age-appropriate dietary diversity. But here, continuing breastfeeding and age-appropriate meal frequency are looking good. And this is the simple tile-based method. So we can do this by tally sheet, calculator, and by hand, and fill in the tiles by with different coloured crayons. And so we can do that by hand. It's not fast to do it that way, but it can be done that way, and it's relatively easy to do it that way. But we can computerize it. Next slide. This is what we get if we move to inverse distance squared weighting for interpolation. So here, rather than having a single value per tile, we've got hundreds, maybe thousands of points of which we've made an estimate, and we've plotted those in appropriate colours. So the red is the poor and the green is the good. Up, and we'll see here as well that that it's down in the southwest corner of this district. This is Bulosasore in southern nations in Ethiopia. We can see that good IYCF practices are at fault there, but also here, moving to a more sophisticated analysis, we can see here that exclusive breastfeeding is also poor there, and age-appropriate dietary diversity is also poor there. And this really needs you to be doing it by computer. You couldn't really do this by hand. There are just too many points to be plotted there. Next slide, please. Here we're looking at fortified complementary feeding supplement coverage of that. This is in southeast of Ghana, in three counties, they call them, or districts. I think they're 3 administrative districts. And here we can see on the left-hand side, we see the message coverage. So have people heard of the product we're trying to get them to use? And the right hand is the contact coverage. And we can see that message coverage is quite patchy, and contact coverage is also rather patchy. And in the central northern district of this region, contact coverage, which is actual, they've used this product this week 3 times, is not very good. And so that's providing us information about where our coverage is failing. And it seems to be it's failing because we haven't got the messaging right. But certainly, even when we've got the messaging right, we're not getting much contact coverage. Next slide. Here we see it again. This is using inverse distance weighting, but the power we're using here is a very, very high power. And what this does, it creates polygons of influence. And so the boundaries between each of these polygons is the exact midpoint between it and the nearest sampling point in that direction. So here we can see that in the eastern district, we're actually not doing too badly in terms of message coverage. And we did quite well in the capital city of the western district. But in the eastern district, we did quite well in the capital. But in the outlying areas, no, we haven't got much coverage. So we can change the analytical method we're using to get a slightly different picture of the spatial pattern of coverage or the spatial pattern need. Next slide, please. This is the product we're using, Cocoa Plus. I think it was produced for gain by a Japanese nutraceutical company, and the point here is that we can produce tables and graphs as we can with any other survey method. And here we can see a Pareto plot of the reasons for non-consumption of Cocoa Plus. This is a typical thing we do in a coverage survey. And mostly they were not using Cocoa Plus because they've never heard of it in this case. When we asked them, have you fed Cocoa Plus to your child, the response universally almost was, cocoa what? They'd never heard of it. And so here we can this ordered list of barriers, we can see the most important barrier here is lack of information about the product. Also, perceived lack of need, lack of information about the need of the product. Next slide, please. Here's an example of a national S3M in Sudan, which we sometimes think of as North Sudan, but it is Sudan. And here we're looking at consumption of iodized salt. And here we've used an LQS classifier to classify, is the coverage below 20%, 20% or below, and that's the orange tiles. Tiles in which it is between 20 and 50% are yellow, and where we've got a satisfactory coverage, which has been defined here as 50% or higher, they're the green tiles. And here we can see that in the areas where there has been mandatory fortification of salt, iodine fortification of salt, and this has been policed to a certain extent by taking salt samples from markets and prosecuting traders that were trading in unfortified salt. We can see that fortification program has achieved reasonable coverage, and they're the areas that are pointed out on the map. And so this was the 2013 Sudan S3M, and mostly we in that S3M we plotted tile classifications. Next slide, please. So I think what we can say is that a spatial dimension is important, and spatial methods needn't be complicated. S3M is as simple as possible. It was proven effective during the CTC research program, and after about 10 years of use. And in fact, the CSAS coverage maps of CTC programming and TFC programming were so clearly different from each other in that we had a much more spatially extensive coverage in the CTC programming. It was one of the key pieces of evidence that informed the switch from centre-based programming to community-based programming. S3M is still simple. The calculations to do some of the mapping are not so simple, but it's still simple. It started life as an improved version of CSS for the Ethiopian government, but it can be extended to a more general purpose survey method rather than just a coverage survey method, as can CSAS. And it's proven useful for needs assessments in programs and M&E in Niger, Sudan, Ghana, India, Ethiopia, and Myanmar. Let's have a quick look at some results now. Next slide. Oh, sorry, going beyond coverage. Yeah. It started life as a coverage method, and it's evolved into a general purpose survey method. A good example is the Sudan National S3M. We've had 2 sub-national state-level pilots and 2 national rounds completed. And that was in 2013 and 2018. So that's the entire northern area that was accessible and some of the borders to the south are inaccessible because of conflict. And in Sudan, it's used in the same role as DHS and mixed surveys, and using the same broad set of indicators in these multiple indicator cluster surveys like DHS and mix. In these surveys, S3M state and national estimates usually agree with the DHS and mix estimates. So at the mid-level, spatial dimension that you only ever get in mixed and DHS surveys, we get agreement. And that in the second national round, we used a variable density sample design. It was an experimental sample design. And this, you collected a finer sample where there was a more dense distribution of population centres. And this created a bias in the sample, so it simply stopped being easily representative of population. And in the analysis of MODA, which is a disadvantage analysis of disadvantage, we found that it was not agreeing with the results from a recent mix. And what we did is we had to post-stratify to weight by locality in order to get agreement. But overall, that you get a map, and if you do a bit of post-stratification, which is not terribly hard to do, you get the same results as you get with the large population samples. And we've done a lot of work on adaptive indicators for use in this with small samples. And many indicators have now been adapted. And many of those standard indicators that we're used to in our surveys, they're already there, they're already done. Next slide. So here's one from the 2018 S3M in Sudan. The grey areas and the areas where the border is highlighted in grey are inaccessible areas. This is where the conflict had kicked off while we were doing the survey, so we couldn't go there. It was unsafe to go there, but we managed to go quite across the entire state. And this one here is the Women's Dietary Diversity Score, and we can see that, as expected from if you have experience in North Sudan, is that people aren't eating a terribly diverse diet. This is 2, 3, 4 maybe food groups in a daily diet. Next slide. Here we're looking at dietary intake, and this is consumption of iron-rich foods. And this is where this is again in carers of small children. And here we're using the Women's Dietary Diversity Score data set. And in that data set, the food groups were organised in terms of micronutrient content, and some of them are organised in terms of iron-rich foods. And so we can use the WDS data, we can torture it if you like, extend its use from a simple score of a simple count of food groups into looking at what those food groups are. And here we can see that there are certain areas of the country where iron consumption in the young mothers is not particularly good, and other areas where it's not so bad. And the work done on this we did with UNICEF and with HelpAge. With HelpAge, they developed the RAM-OP survey method, which is a cheap and dirty smart survey, but they wanted to tease out the micronutrient intake from a dietary diversity score indicator, and we did that work with them. Next slide, please. This is nutrition anthropometry. So this is weight for height Z score less than -2, and we can see that in that Red Sea state in the east is not so good. I think there's Nile state in the next to it, and then as we approach the Darfurs, we're seeing higher prevalences of moderate wasting by wake height Z-score. Now, the previous SHHS, which is the Sudan Household Survey, which is the equivalent of the DHS survey or mixed survey, that only produced state level estimates. And I don't think it would have given us a very different map. I think we'd have detected those red areas even in that course mapping. And the national SMART was usually limited to locality, which are district level estimates. And I'm not convinced it would have given us a very different map. But we can see here the distribution of wasting is not homogeneous over the country. Next slide. This is using the 2013 S3M data, and one of the immediate uses of that data was to reform the CMAM programming. And here we've identified the locations of existing CMAM OTP sites, and we've identified areas of high prevalence of severe wasting by metabarometer circumference. And we've decided to open an additional 4 sites at existing healthcare centres to attempt to bring the programme closer to areas where there are high levels of severe wasting. And this was done, this is West Darfur, I think, and this was done in all of the areas in which there were operating CMAM programs, which was not all of the states in Sudan, but it was all of the Darfur states. It was Qatarif, it was all the states north of Qatarif, which was Red Sea states, and gone out of my mind now. But it did allow us to alter the programming to match need that we've observed. Next slide. Here is this is an early use of S3M, and this was the post-Nargis joint assessment. So that's Cyclone Nargis coming into Myanmar that caused tremendous devastation. And this is round 4, so this is 4 years into the rehabilitation program, and we can still see here there are a large number of households where there has been complete destruction of housing, of dwellings. And the first round, we were not so experienced with using S3M. And the first round would use CSAS. And so the next slide is the 4 years earlier. This is the village tract assessment, which used CSAS. And we can see that CSAS has done quite well. We can see the track of the cyclone, and we can see that the cyclone actually tracked to the higher above the red area here. And what we're typically seeing here is the dangerous semicircle of any hurricane force wind, and this matches expectation of the programming. And these maps were used to inform programming design and to direct funds particular activities in particular areas, direct NGOs to deliver services of particular types in particular areas. So CSAS, the very simple method, which you can do with a ruler and some crayons and a calculator. It actually does quite well. I think the feature detection is not likely to be as good as with S3M, but it's still functioning quite well. And is there a next slide? That's me done. So here's a piece of artwork about mapping of emergency activity during the the early years of the Second World War in the UK, which would have been an era of prolonged aerial bombardment by the Luftwaffe. That's me done.
Great, thank you so much, Mark. And that was a really wonderfully clear, and I think we have 15 minutes for kind of Q&A and discussion. I know
Excellent.
that
I got there on time. I usually talk too long.
Great. So again, we encourage people to go ahead and write your questions in the chat. I know we have a couple. I have a couple back pocket questions, but would really encourage, we have a relatively small group, but that also means we can have a bit more of a conversation. So starting off, and I think there's two questions from Anne Swindale that are, I think, really follow-ups on your Ghana example. So I don't know if we want to move back slide-wise to that example, Riley, if you're able to.
Okay, I can answer that.
Yeah, so why are the darker colors? And then what was the total sample size and how were they selected?
Right, okay, so what we did in this one, so this is using inverse distance squared weighting. When you use inverse distance square weighting, that what happens is you focus quite closely on the points closest to the estimation you want to make. So that field you're seeing in the map on the left is maybe you know, it might be 10,000 points that are being plotted there, and each point getting a colour. So we pick a point and we base the colour of that point on the values at all the points, but those nearest points get more weight to the furthest point. So you get this sort of clustering around the points. And what we've done, and inverse distance squared is a very common interpolation procedure, but it does have this. I'm not sure it's weakness, but you know, it does have this effect that you do see this clustering of these reds and these greens around the points that are red and green. Now, what we've moved away from using this to using an inverse distance weighting, where the power used in the weighting is detected by a validation exercise. So what we do is we take away one of the points, one of the sampling points, and then we calculate what weighting power gives us the right answer. And so we might end up, rather than 1 upon the distance squared, we might have 1 upon the distance to 1.3 or something, or 1 upon the distance cubed. But it gives us a presentation which is more accurate, I think. Inverse distance squared is a general purpose, the first tool you reach for, the other powers are finessing that. Now, of course, you might choose a very high power if you're interested in producing Voronoi polygons, and which is what we have in the next slide. There we are. So what we've done here is we've used a very high power, and what this does is it creates Voronoi polygons, and this would give you the area around each point is the value at the point where we measured it. And it's a simple and easy way of doing a spatial analysis. This spatial analysis is done mostly in retail geospatial analysis. So we're identifying catchment areas of shops or catchment areas of gas stations, catchment areas of schools, if you like, as well. that's what it's showing us there. And I don't think it's terribly meaningful here, as these are not market towns. These are not the effects of different markets. These villages are selected spatially, so they're not even necessarily big villages. Some of them could be very small villages, but it gives you a slightly different picture of what you get. Now, what you could do is you could use a much more sophisticated mapping method, such as Kriging, which is used in mineral exploitation. And you could use that, and that's not terribly much more difficult to use.
Thanks, Mark.
Go ahead, Rebecca.
Yeah, so I think super helpful specificity, and I'm going to draw us back to a higher level kind of question. But first, I do think, Anne, Riley, were you going to give Anne a chance to follow up on her questions?
Yes, Anne, you can go ahead and unmute yourself and ask your question.
Great, thank you very much. Thanks, Mark. This is great to see this sort of progression from that earlier work. So the previous slide, you said it's sort of an artifact of the weighting process that was used, and so in the end, it can give you a distorted picture, right? That it says either things are much better off or much worse off around those points, and then the surrounding areas are either a little less well off or a little less worse off. So is this approach something that you basically no longer recommend that people use? And then on the next slide, you said that this presentation is not as useful because you're not really working with catchment areas. So if it's less useful, why are we looking at it? And how would we use it? Would we not consider this to be a reliable estimate of the fortified complementary feeding supplement coverage? Thanks.
They are pretty reliable estimates you're getting. I mean, there's no real reason to think that if I go to one village and I find that coverage is very poor there, that if I walk a few hundred meters out of that village, that I'm going to find very, very different coverage.
Mm-hmm.
I think that what you get with the triangular grid, which you don't get so well with the square grid, is you get what's called feature detection. So you tend to be able to pick up high points and low points quite well with the triangular grid. So you do get a better map. Now, would I recommend anybody using inverse distance squared weighting? I certainly wouldn't recommend them not using it. It is the go-to, and has been the go-to interpolation that has been used since the 1960s, and it's the sort of interpolation that you would get in ArcGIS or something. You know, a top-end geographical information system would do that as a default interpolation method. And they'd also have more sophisticated interpolation methods, but they would do that. I think what we would do now is we would have a look at the inverse distance squared, but also work out what power gives us a better accuracy. And by accuracy there means if I take a point out of the data and a sampling point out of the data, and I make the map, at the center of the removed data point, what value do I get? And how close is that to the value that I saw in the removed point in the survey? So does it fit the data? And that produces a better surface, and it gives more accuracy at each sampling point. So that might be something we might do.
Thanks. Anne, do you have any other follow-up on that?
No, that's okay for now. I'm just trying to wrap my head around it all.
Yeah, well, as am I. So maybe with that, Mark, if we could just maybe pull back a little, would love to get your take on maybe two things. One is that, and you've talked about, and I think we know that the emergency community has really picked up on a lot of these methods. And I think with the emergency community, there's a really strong emphasis on, I think, program planning and data use for making these decisions. And we know that some of the kind of more distant geographical pockets might be places where coverage isn't reaching, although you've also been showing us some great examples of other indicators that are kind of relevant a little bit more on the development side as well. But kind of traditionally, the development sector has really relied on things like the DHS or the mix or these national health and nutrition surveys that use more population proportional to size sampling methods. And so, if groups are thinking about things like, well, what if we use this method for a survey? How comparable could it be to the data we already have, for example, from the DHS, because their interest is actually tracking trends and changes in coverage over time, or they're, trying to respond to their national monitoring framework where they need a national estimate of coverage as well as this. So the people who are program planners, but also have this focus on monitoring and targets and tracking. What would be some of your thoughts about the comparability of estimates from things like the DHS at the higher levels with this approach? Has there been work doing that, or is there anything you could say about that?
I think that what we get is from the S3M design that I presented in it just here, without the variable density sampling, but just with the uniform density sampling across a wide area. That what you do is you treat it as a stratified sample, and then you treat it as a stratified sample. So you calculate, you estimate something within each primary sampling unit. And then you combine those results, weighting by the population of each primary sampling unit. So we treat it as a stratified survey, and the results that drop out are very, very similar to the results that come out at national level, very, very similar to the results that drop out from Mix, DHS, and National Smart. But if you go more sophisticated, you start sampling more densely in more densely populated areas, it starts giving you wrong results, and you have to be aware of the risk of that happening, and then post stratify, as you would in many other surveys, post stratify, and that will give you the results the same as a PPS.
Great, so that there are methods to analyze the data in a way that would give you comparable estimates.
Yeah, I mean, it's a survey, and right. You can make it, but what we're doing here is we're not stratifying, we're not designing the survey to give us a population representation. We're designing it to give us a spatial representation. And we deliberately design it not to give us a population representation, but a spatial representation, because those PPS type samples then tend to place the sample in specific locations, and those locations are the larger villages and the towns. And if you're looking at coverage, that's going to give you a strong upward bias. Whereas if you're looking at some prevalences, that might give you a downward bias. And you certainly would miss areas of high prevalence that if they weren't brought in to, because we know disadvantage. We know disadvantage occurs in peripheral communities, and so if you have a sample that by design biases you against taking samples in those peripheral communities, then you will get a bias. And it will be a bias, a different bias. And so all of those survey methods are biased. And so I think what you're asking me is can I make this survey method be biased in a similar way to the mix and DHS and SMART methods? And yes, you can. You can, and you have to know that that's what you want to do.
Yeah, so I do. I think this is really helpful to emphasize, and Anne made the note that this is a fundamentally different method of sampling than a population proportional to size, and that all of these sampling methods have trade-offs as you think about the application. And so I think as we continue in this series, where we really do hope to continue to build on this discussion of considering, you know, what are the features and for what purposes, and as we think about bringing in them together, you know, what are some of the implications? There was a follow-up question about rural versus urban samples that I'm going to ask Mark, if you're willing, we could answer offline, and then we'll post that as part of our.
No, yeah, I can do that now. I
Yeah.
can wave my hands about that. Yeah.
Okay. Well, I also want to make sure that folks who need to finish, because we are hitting the top of the hour. But okay, go ahead, give a quick answer to that, and then I'll wrap this up. So Andrew said that he'd like to hear more about the application of these sampling approaches to urban samples. Are they more useful for rural areas?
We have one of the motivations for using the variable density sampling method was to let the sample smoothly merge into big conurbations. So looking at Ghana and looking at India and looking at Sudan, some of the cities there are truly enormous, both in terms of the area covered, but also in terms of the population there and the population density. And so the variable density sampling method, it increases the density of the sampling as you move into cities. And what you do is you then use a natural sampling unit. So you locate your sampling unit with regard to the triangulate irregular network, and the PSU the PSU drops into a location, and you sample the city block that falls into. And sampling a city block is relatively easy, in that you can use what we tend to use is the census enumeration area maps, or we do simple on the ground mapping, and we do systematic doorway sampling. So we take a systematic sample over the entire city block, and that becomes the sampling point. It becomes a sample at the PSU. And that works reasonably well. It works reasonably well, but I think that we haven't got enough experience with the variable geometry sampling method to enough experience with it to actually say there are no negative side effects.
That makes sense. That makes sense.
And I think that what we have found, I think, is that when you're looking at, you know, the problem with any systematic sample is that if something varies along with the way your systematic sample is taken, then you can run into problems. So one of the early problems we saw with the CSAS method was it wasn't terribly staggered, and we ended up with samples that were taken. I think it might have been Burundi, and what we ended up with samples that were taken all at the tops of hills and not in the valleys, because the way that the 10 by 10 squares located the sample over the survey area. So we actually ended up with something very different. And I think what happened in Sudan is that because as we approached very large cities, and there are quite, you know, the cities are very large in Sudan, Khartoum is enormous, is that what we did is we ended up with more sampling points, more sampling points than we expected being taken from cities, and this gave us an overestimate of the coverage of the education indicators.
That makes sense.
Was a specific problem, yeah, and we had to fix up the sample.
Right, and then you need some sort of reference that's telling you that is a problem as well. But
yes, I mean the classic example is if you've got a list of people who live in a household, and a list of people live in an area and they're organised by surname. As you move down that list, you tend to get married couples close to each other and unrelated couples distant from each other, and so you skip over all the women, or you skip over all the men, and you end up with a biased sample. And I think that what happened is that we ended up with a biased sample where the sampling locations, the way the sampling locations were decided, coincided with how one or more of the indicators were distributed.
great, thanks so much, Mark. And again, we will have an opportunity to do a little bit of follow-up with the Q&A. And also just want to remind folks that if you are interested in this issue of sampling methods, we're going to have an upcoming webinar, we hope within the next month or two, but are still confirming the date, that's looking at a comparison of geosample methods to more population-based sample methods that was done under the RADAR project by a team at Johns Hopkins in Burkina Faso. So we're really excited because I think that, Mark, you've provided a wonderful foundation of understanding of the geosample method and some of the differences, and that this next webinar will really be able to take us another step there in looking across as people consider what is the right sampling approach for their purposes. So thanks everybody. Thank you everyone.
I've just got the Ghana data in front of me now, and I'm looking at it, and there are 58 primary sampling points, and we have 971 individual records.
Great, thanks, Mark, and we'll be sure to add that to the Q&A. All right, thanks everyone, and we look forward to joining in with us the next time. Bye-bye.
Okay, good.